Welcome. This is Chris, and as I promised, here is a overview of the Dijkstra's algorithm and the A Star algorithm, which is going to be useful to you to finish up the Trailblazer assignment. And what I'm going to do is go through the slides which are for the lecture for next Wednesday, which is May 31st. But I'm going to put these up here now just so you have the idea so that you can get started on that part of the assignment if you want. Most of this information will be repeated in Wednesday's lecture. All right, let's get going. So first of all, let's just review what we talked about on Friday, which was the depth first search and the breadth first search. Now, these are searches that are simply based on either going deep along a particular path. In other words, you keep searching along a path. So if we're going from 0 to 6, you can go from 0 to 3, and then you would keep going along a path, and you'd say, okay, now I'm going to go to all the neighbors of 3, so I'm going to go 3 to 1, and then 1 to 6, and that's the depth first search. Okay, another depth first search might be 0 to 4 to 6, or something like that. A breadth first search is actually saying, look, first look at 0 to 3, then look at 0 to 4, then look at the paths that are 2 away. So we might go 0 to 3 to 1, and that's not there yet. And then we'd go back and go 0 to 4 to 6. So that's a breadth first search. Now what we're going to talk about today is very similar to a breadth first search, except the difference is now we're going to actually have weights. The depth first and the breadth first did not deal with weighted paths. They just dealt with hops to neighbors, not based on any particular amount of time or distance or what have you. So now we have to start thinking about how do we get path lengths, in other words, the shortest path from one node to another that does depend on how much a particular edge weighs. Okay, so this is now the difference, and this is where the other algorithms are going to come in. So first of all, let's just do a little quick search on this very easy graph here. If we want to get from A to D, well, pretty simple. We go A straight to D, and that's the shortest path. Well, that's nice if there's no weights on there. Okay, A to D, shortest path. However, if we put paths on here, or if we put weights on here, well, look what happens. Now, the shortest path is not A to D, because that would be 12,345. The shortest path with the weights is now A to B to C to D, with a total path length of 10 plus 5 plus 3, which is 18. Okay, so the path length here is A, B, C, D, and that's now the shortest path because we're assuming that the numbers here designate, let's say, the distance between the two. So this might be going over some giant mountain to get to from A to D, and this way it's going around some other path. Okay, so this is what we have to think about, and this is what we're going to do. Okay, breadth first search would break on this, depth first search would break. So it would definitely break on this because those don't take into consideration any weights. All right, so recall breadth first search. We use a queue to enqueue each path, right? We start from A, and then we enqueue all of the neighbors of A. In this case, it would be A, B, and A, D. And we're going to do the exact same thing, except now we're going to have to prioritize based on the path length. Now, if we start to think about prioritizing and queues, well, guess what? You're going to start thinking of using this thing called a priority queue, which we have dealt with for the last few weeks. And if you use a priority queue instead of a regular queue, you get this algorithm called Dijkstra's algorithm. Dijkstra was a computer scientist in the late 20th century, and he came up with this algorithm first. Okay, and so with Dijkstra's algorithm, what we're going to do is we're going to use a priority queue in place of a queue, and it's surprising that it actually works out exactly the same as the breadth first search, except for the fact that now we're using a priority queue. So there's nothing too difficult to learn about this if you already know breadth first search. Okay, so this is the breadth first search algorithm. Remember, we started a queue of paths, and then we enqueued a path, and then went into this while loop. Also recall, this is the same exact algorithm as a level first tree search, but it's called breadth first search. And remember, we enqueue a path, and then go into a while loop, dequeue that path, take the last element of the path, and then look at all of its neighbors and re-enqueue paths based on that. And going along, you also have to mark the edges as visited whenever you get to one that you're looking at, such that you don't go into any cycles. Okay, but we're going to do the exact same thing, except now Dijkstra's is simply going to use a priority queue. So if you'll notice, I'll go back and forth between these two slides. The only thing that's changing is we're using a priority queue. So there is nothing different. The only caveat is that breadth first search, you can actually stop a little bit early. For Trailblazer, you're not going to want to stop early just so that the algorithm continues. But if you do stop early, you can, because once you get to a node and you realize you've actually found the final end node, you can stop. Dijkstra's, you can't quite do that, and we'll see why as we go through this example. Okay, Dijkstra's algorithm is what we call a greedy algorithm, which means that at any particular time, it greedily picks the next path that's the best one at that particular point. So in other words, if you're going from A to D, the greedy solution says, oh look, there's a nice short path from A to B, which is 10, and that's a better path than A to D. It's another way of saying that we're prioritizing this. Okay, and that's how when the priority queue comes into play. Okay, so let's actually do this example. Now, this example is one of the ones you're going to want to go over a couple times here, and I'm going to go over it relatively slowly here, and you'll see how it works as we go through. But it's going to look very similar to the breadth first search that we did the other day in class. Now we're just going to have to use a priority queue, and we're going to update the queue, or when we enqueue, you'll see that the new paths go in priority order. Okay, so we're trying to get from A to I, and we're going to start by enqueuing the path of just A, which has so far a distance, or a total cost rather, of 0, because there's no actual edges to calculate yet. Okay, then we go into the while loop, and in the while loop we dequeue A. That was the first one we had on there. So we dequeue A, and then we take the last vertex in the path, and we get all of its neighbors and update the priority queue based on those new distances. Okay, so from A, we've got A and B, which has a cost of 6. 6 plus 0 that we started with is 6. So AB goes into our priority queue with a priority of 6. AD goes into the priority queue with a priority of 3 because it's less. Now, the nice thing about a priority queue is that we now have the next one that's going to be dequeued is going to be the one with the highest priority, in other words, the lowest number, which in this case is AD, so it's going to greedily pick the AD. Okay, so then we go on, we dequeue, and what do we get? We get AD out of the queue. Okay, we get AD. It has a priority of 3, and then the last element in it is D, and we are therefore going to look at all of D's neighbors that we haven't visited yet. Notice we've already visited A. So we're going to go from D, and we're going to go D to E, and that's going to add one more to our current cost. Now, how much does it cost so far? Well, A to D has a priority of 3, so then we add one more, and now we've got a priority of 4, so the path ADE is going to go into our priority queue with a priority of 4. Okay, and we also have ADG, which is going to go into our priority queue with a priority of 12. And notice, this is how the queue ends up. We just put in ADE with a priority of 4, and AB was already in there, but it had a priority of 6. So we are not going to greedily, or we are going to greedily take out the next best overall cost, which means the next thing that comes out of the queue is going to be ADE. Okay, you'll see that this isn't necessarily the correct choice, but it's the best choice so far given the fact that, given what we know so far. And notice ADG with a terrible priority of 12 goes into the end of the queue. All right, so we're going to DQ ADE, okay? ADE comes out, it had a priority of 4, and now E is the last element in that priority, and therefore we can now look at the neighbors of E, okay? And you look at E, and we've got EB, and EF, and EH, and we have to put all of the paths up to that point in there. Okay, so we're going ADE, ADE, and then let's put in ADEB. Well, ADEB is going to be the current priority so far, which is 4, plus the cost from E to B, which is going to be 5. So ADEB goes in with a priority of 5. Happens to be a pretty good priority, actually, the best so far. Then we put in ADEH, and why is that 8? Because it started with 4, and there's 4 more from E to H. So the priority now is 8, and that's where it goes in there. The last one is ADEF. We started with a priority of 4 to get to ADE. We add 7, and that goes in with a priority of 11. So these ones in red are the ones we just enqueued. Well, which one comes out next? So it's got to be ADEB because it's got the highest priority. And ADEB comes out with a priority of 5. And therefore, the last element is B. And ADEB, the next one we put in is C. And C hasn't been visited yet. So we can actually put, excuse me, we can put C in as ADEBC, ADEBC with a priority of 5 plus 3, which is 8, and that goes in there. Okay, so then AB comes out next, and AB has a priority of 6, and then we get the current path. The last element is B, and therefore we can now put ABC in there. So again, we put C in there because it hasn't been visited yet, so it just gets continually updated there. And which one's going to come out next? ADEH, and therefore ADEH with a priority of 8 comes out. Now, interestingly, ADEH does get to I next, but it may not be the highest or the priority of the minimum path yet. So we can't just say, let's stop now because we've seen I. So you have to be a little bit careful here. We just enqueue it as normal, ADEHI, and we'll see. It may become the shortest path, it may not, but we have some other things to deal with before we get there. Okay? All right, so then ABC comes out next, and that's got a priority of 9, and therefore we put ABCF in there, and that goes in like that. Okay, and then that's the only one we can put in. So then the next one comes out as ADEBC, and that has a priority of 8, ADEBC, and then the only one we can put in now is F, but look at this, ADEBCF has a priority of 9, which actually means it's going to go right at the front of our queue. So, so then we pull ADEBCF out, which has a priority of 9, and then we can actually add the I, but again, we can't stop yet. And we can't stop yet because we don't know if that had been very low, it might have actually beaten the 13 over here. If it had been a 1 or something, then this path would have beaten this path. It's not going to, as it turns out, but it would have, and therefore this would have been a shorter path. So, so we do need to enqueue these things until we pull one out where the last node is the one we're looking for. Okay, so we keep going. ADEHG is going to come out next. ADEHG has a priority of 10, and its last element is G. D and H have already been visited, so we don't enqueue anything. Okay, and then ADEF comes out. ADEF has a priority of 11, and ADEF has a priority of 11. Well, we can add the I in there. It's going to be another 18. So we've got another one with I. So eventually we're going to get there, right? We're going to DQ one that has that. But again, if that was lower than the priority of these ones, that would have been the lowest path. And we would have eventually gotten that out because of the priority queue. Okay, now, sorry, that we do have something to enqueue here because the neighbors were visited, because ADEFI is in there. Now, we can keep going. ADG is going to come out next, and ADG has a priority of 11, but then again, we don't enqueue anything. And then finally, ADEHI comes out with a priority of 13, and that's the shortest path, ADEHI. Okay, not intuitive that that's the shortest path. It happens to be, in this case, the shortest path, but the algorithm got us there. Okay, and it's the shortest path by virtue of the fact that the weights make it the shortest path. Okay, that's Dijkstra's algorithm, and that's how it works, and it's pretty straightforward, all things considered, if you already know breadth first search. You just have to change to a priority queue, and remember to not dequeue or to not stop when you finally found that node. You have to stop only when you pull it back out of the queue, and the last node in the path that you pulled out of the queue is your end point. Okay, that's Dijkstra's algorithm. All right. So it turns out Dijkstra's algorithm is great, and it does work, and it will give you a shortest path. However, it's not the fastest way to do that, okay? Notice it's still breadth first search, and it still searches locally around a particular node. And while that's not bad, it's just not necessarily going to be slow. Turns out we can add more information for many types of searches. For many graphs, we have more information that allows us to preferentially go in a particular direction. Okay, so take an example of going from Stanford University to San Francisco. Well, we know by virtue of the fact that we understand maps and how they work, we have got to go northwest. Okay, the idea is from Stanford, you're going to go northwest. Well, what we do in this other algorithm that we're going to call A star is that we say, wait a minute, don't just use the priority of the particular neighborhood. Use the priority of the particular neighborhood, but also preferentially choose the direction to go based on the direction we know that we will eventually end up. It doesn't always work perfectly, but as long as you know something, some more information, we can do better. Okay, so let's see how that works. Now, let's go back to Dijkstra for a minute. We're going to see it a little more graphically here. We're going to try to get from between these two stars if we only had an edge cost of 1. Now, by the way, that happens to be breadth first search, but it's the same if we consider it a Dijkstra. So let's see what happens here if we know that the edge cost has 1. Okay, we start here, and then we mark it, and then we have our neighbors, okay, and let's say our neighbors are just north, south, east, and west, and our neighbors are going to have a distance of 1, and we are going to treat them all the same in the sense that Dijkstra does not care that we actually want to go to the right over here in the end. Dijkstra doesn't care about that. We end up looking at that, so we can look at the order, and we look at all the ones around us like this, and then we start doing the ones with 2 around us. Notice what's happening here. We are spreading out from the star here in kind of a bigger and bigger circle, and eventually we'll find our end here. Okay, so if we keep going, we're going to keep going, keep going, keep going. We're almost there. There we go. Okay, and now we have to wait till we pull it out, and when we finally pull it out, then we know that we're there. Okay, so look at this graph for us, or look at this diagram for a second, and see that it's very much filled in here based on just continually going out one by one by one. But we know, because of the fact that we can look at this and go, hey, wait a minute, going from this star to this star over here is going to, from the left star to the right star, is going to give you a direction. Like, we know it's to the right. So why don't we do something about that? Okay, and we don't need to look in this direction. We can just look in the right direction. Okay, so for priority for Dijkstra, what we do is we basically say the distance plus whatever future cost we have. Now, this is actually an interesting one. There is some future cost that we don't know about that we're going to get to. So we're going to go between S and T, and we know that our next hop might be U, but we could actually, we're going to have to calculate eventually some other future cost, but maybe we can guess about that. Maybe we can say, hey, let's make a added amount of cost based on the fact that we know the particular direction. Okay, so the ideal priority is the actual priority of that future cost plus the distance we already know, right? Which is actually kind of interesting. If we could somehow figure out that future cost by magic, well, that is the ideal priority. Okay, so here's what we're actually going to do. On a map like this, you can actually determine some future cost by the number of columns away from your end destination and the number of rows away from your end destination. It's called a heuristic, and a heuristic means we're going to take the wherever we are and say, if I want to get to a particular place, let me just add the columns and add the rows to that, and that will give me the direction that I have to go, a distance extra that we add on based on the idea that we know some information about the direction it's in. Okay? So in this case, we've got some function which is just going to be the number of rows difference and the number of columns difference. We're going to return that. This is saying from wherever we are, getting to where we need to go has some particular added cost, and we're just going to basically make that assumption, and we're going to add it to our actual goal. So let's see how this actually works, okay? Here's the same thing as before, except now we're going to add on from whichever node we're looking at that heuristic that we just calculated in the previous slide. Okay, so here's the Dijkstra. Each one is one away from us. We know that. But this one is how many, in this case, columns apart? It's 1, 2, 3, 4 more to get there. Okay, 1, 2, 3, 4 more, and we are then there. Okay, so we can add that 4 to this. Now let's take a look at this one. This one is not 4 away. It's actually farther away. We went in the wrong direction a little bit if we went up to this one. This one is 1, 2, 3, 4, 5, 6 more, and therefore we can actually add 6 to that. Notice what we've done. We've said this one is the one that actually is a better choice than this one because it's closer to our goal. So that's the thing. Okay, let's keep going. This one's also going to be 6, okay? How about this one way over here? 1, 2, 3, 4, 5, it's also 6 if you kind of go back towards where we came from. Okay, so the best one in this case is this one, and that's the priority we're going to put in there. So basically, instead of adding 1 to the priority, which we would have done for all of these, this one we're going to add 1 plus 4, this one we're going to add 1 plus 6, this one is going to get DQ'd earlier because we've given it more information. So this algorithm is now going to do Dijkstra, but with the added benefit of going in this direction, preferentially. May not work. We'll see when it might not work exactly, but that's going to be it, right? So now look what we've done. Now we've said we're going to choose that one next, and now how are we going to do this? Well, this one, this is 1 more than this one, so this is 2. This is 1 more as well, 2. This is 1 more, but the distance from here, 1, 2, 3 more. This is from here, 1, 2, 3, 4, 5 more, and 5 up here. So guess what? This one's going to get in queued with a priority of 5. Okay? Notice you have to subtract out the added extra. You're going to have to do this on the homework assignment as well. Okay, and then we do that. Okay, now they're all 1 more away. 3 now. 2 plus 1 is 3, but this one's only 2 away. These ones are 4 away. So we're going to keep doing this. Notice, as we keep going, we are going in the direction we want to go, right? And we're there. We did not have to deal with all the stuff on the left, top, and bottom because we preferentially said, let's just keep going in the direction where we know the result is, and that's the heuristic, okay? That was what A star is all about, and it's actually not too bad. The tricky part sometimes is coming up with that heuristic, okay? Now, what happens if we actually had an area we couldn't go, right? So, in other words, we can still calculate this distance, but in this case, we're going to have to go around these blocks. Like you can't go there in this case, okay? So remember, we've got this ideal future cost, okay? But we have to kind of underestimate it. In other words, we don't know exactly what the future cost is because we could have to go around something. Notice if we go here, the future cost from here would be 1, 2, 3, but it really isn't. It's actually 1, 2, 3, 4, 5, 6, 7, right? You can't go through if you can't go through this block, what happens is you end up saying to yourself, oh, okay, I want to underestimate which way I have to go, because if you overestimate it, it turns out you won't necessarily go in the right direction. Okay? So we always, when we're coming up with these heuristics, we always underestimate the cost of this. I'll have more to say at the end of this as we go along. Okay? Now, what would this end up doing? This ends up making it so that the paths are generally better, but not always perfect, because you have underestimated. So you can't do perfect because you don't have magical information. So we're still going to get a good path out of this. So let's see how this one will work with A star. Okay, let's see this one go. Okay, we're going to do this. We're going to do the same rows and columns apart business. Okay, it's what we call the Manhattan distance. Okay, and in this case, here's what our priority queue did before. Okay, now we're just going to add in that neighbor that we're talking about. So we already kind of saw this here. And we're going to actually add this in. Let's see how it works. Okay, we start here and we say, okay, 4 away. Why is this 4 away? Because if we could go past this block, and we don't necessarily know that block is there, but if we could go past that block, 1, 2, 3, 4 away. Same thing as before. Okay, we keep going in that direction. All right, same thing. Well, now we're going to go there. And we're going to start to look, but guess what? Our only neighbors are this way and this way. Okay? Well, now we have to kind of go back to, we're going to end up back at the other one that we didn't pick before. Okay? And we're going to kind of do that. And now we're going to have to, in the end, wrap around. Okay? So this is giving us some more, this is helping us because we're kind of preferentially going this way. But if you hit a wall, it's not necessarily going to help you, because there's the priority queue is going to still start looking at things over here because it has no idea that there's a wall there. And in other words, you've got the priorities. If there's not a priority that's going to keep you going in the same direction, you do still have to do some looking in the back there, okay? So we're still doing this, and now we have to search a little bit more because we have this silly wall here, okay? But now that we get here, we're going to say, aha, now we can start going in the correct direction, and the priorities are going to in the end, get us there a little bit quicker. Okay, this is what it would have looked like if we did Dijkstra before, by the way. But the nice thing is, we still, because even though we had this wall here, we didn't have to do as much searching as we would have had to do with Dijkstra. Because remember, Dijkstra doesn't care at all about direction, and in this case, because we had the extra information, we could do that. Okay, all right. Again, we'll talk a little bit more about the actual underestimation. But the idea is there's only so well you can do. You can't overestimate the direction, because that would in some cases send you in the wrong direction. Okay, so in this case, from this node here has a cost of 11, right? Why is it 11? Because it's the 3 plus the 1, 2, 3, 4, sorry, 1, 2, 3, 4, 5, 6, 7, 8 to get there, okay? And so if we overestimated it, let's see, how might we overestimate it? Well, let's say we thought, well, let's always just say that the direction we want to go is more. Well, then that's going to end up over prioritizing based on thing, and this one would come out next, and you would not have a good heuristic. So always underestimate it. Now, let's quickly look at the differences if we did if we made the heuristic 0, if we underestimated, if we somehow had the perfect distance, and if we overestimate. Let's actually talk about what that means here. Okay, so for A star, if you have a heuristic of 0, isn't that just Dijkstra? Remember, Dijkstra is, or A star is Dijkstra plus this heuristic at each stage. Okay, so you add in the heuristic, and then when you get to that point, you discard the heuristic that you, or for the last time. You can't, by the way, you can't keep adding heuristics one after the other, or you will overestimate again, and you'll end up not having the right priority. So basically, the idea is do the Dijkstra algorithm, add the heuristic, and then the next iteration through the while loop, subtract out the heuristic and add the new heuristic. Okay, once you do it for Trailblazer, you'll see what I'm talking about here. But that's if we have a heuristic of 0, it's just Dijkstra. If we underestimate, this is A star. Now this will find the solution in the same amount of time or faster. Okay, you might have a terrible heuristic and it just takes the same amount of time as Dijkstra. But if you have an underestimate and it is a good estimation, then you will find the shortest path, same as Dijkstra as it turns out, but you will end up finding it faster by running your algorithm. Dijkstra would have taken longer to find that shorter path, that shortest path. A star will also find the shortest path, but will do it faster. Okay, if for some reason you had a perfect distance heuristic, okay, that means you'd always know the best path. Now, this requires perfect knowledge, and if you had perfect knowledge, you would already be able to figure out the algorithm without having to do an algorithm. You would already be able to figure the distance out if you knew the perfect knowledge. So there's no perfect knowledge. Now, sometimes, if you overestimate, remember, you actually might not find the shortest path. You might actually find a path to get to the end that's not the shortest. By the time you DQ something with the end node being the node you're trying to end at, because you've overestimated the heuristic, you may end up having a path that's not the shortest, as it turns out. Okay, now that might actually run faster though as it goes. And there are times where you may want to overestimate. So for instance, in game design, sometimes for multiplayer games, they're trying to estimate how the entire game is going. And sometimes they won't need the speed of figuring out a good enough solution, but it might not be the best solution, but it's good enough because it's faster. Okay, so that is Dijkstra and A Star, and we'll see more about this on Wednesday's class. Okay, all right, and finally, this is what A Star looks like in real life, which is kind of cool. All right, thank you very much, and I will have more for you guys on Wednesday. Thanks.